For another example of a line integral, let's find the line integral over c of 2x ds, where c is this curve drawn below. So we've got this parabola region from 0, 0 up to 1, 1, and then we've got a straight line from 1, 1 up to 1, 2. So in this one, what we're going to need, if we think about that formula for our line integral, is we need a parameterization. So let's try and find a smooth parameterization for this. Now, probably the easiest way to do that is to do a piecewise smooth parameterization. So we'll have like curve 1 and then curve 2. So this is what we were doing before. So curve 1, we need an x of t and a y of t. It needs to follow that parabola shape. So in rectangular coordinates, this would be y equals x squared. So remember, one of the easiest ways to do this is to let x be our parameter and then let y be the function in terms of x, which is now t. And since this is the first piece of our curve, we don't need to do any adjustments to that t. If I just let t start at 0 and stop at 1, then this will follow that little parabola curve from 0, 0 up to 1, 1. And then our curve 2 will need an x of t and a y of t. Now notice x, so we're going from 1, 1 straight up to 1, 2. So x just stays constantly 1. And then y needs to increase from 1 up to 2. Now notice that what we actually want here is t, my last piece, stopped at 1, and this one needs to start at 1, and then go to 2. So actually for t to vary from, or sorry, for y to vary from 1 to 2, we can just let y be t. So what that means then is my curve is really r of t, is this piecewise curve. We go from, the first piece would be t I plus t squared j, and that's for t from 0 to 1. And then our second piece would be 1 times I, so just I, plus t times j, and that would be for t from 1 to 2. Now if we think about when we're coming back to this integral over c of 2x ds, and we think about what we're going to have to put in our new integral, well, part of that new integral needs to be the magnitude of r prime. But notice that the function that I use for r changes depending on what interval we're over. So just like with regular functions, if I was trying to integrate a piecewise function, what we would do is we would split it up over the integral. So what we're doing here is we've got a piecewise curve, a piecewise parameterization for our curve. So we're going to split up over those two different integrals. So we'll first integrate from 0 to 1. So from 0 to 1, because I guess what I'm trying to point out is if in total we want the integral from 0 to 2 of that f of xy, and then we want times the magnitude of r prime. But this magnitude of r prime is going to change depending on where we're at. So if we do from 0 to 1, f of xy, well here, x is the function, we're using the top piece right now. So x is t, and then we'll have the square root of x prime is going to be 1. So we'll have 1 squared, and then y prime is going to be 2t, because it's this derivative of t squared, so we'll square that. And then that will be dt. And then notice, though, that I still need to then pick up my next integral, which will go from 1 to 2. Here, x is the x component, which is 1, so it'll be 2 times 1, times the square root of x of t is 1, so x prime is 0. And then we have plus y of t is t, so y prime is 1, and we'll do that squared. dt. So when you do have a piecewise smooth curve, you're going to have to break up that integral over those different pieces. So let's just simplify these. We'll have the integral from 0 to 1. We've got 2t times the square root of 1 plus 4t squared dt. And then plus the integral from 1 to 2. We've got 2 times the square root of 1 squared. So all in all, just 2 here. And this will be dt. So now we have to do each of these integrals. In the first one, notice we've got a square root of 1 plus 4t squared. But on the outside, I do have 2t, which is excellent. So if we do a u sub of 1 plus 4t squared, that's going to make du 8t dt, which I do have 2t dt. So if I solve for 2 dt, then we're going to divide a 4, so that will equal 1/4 du. You could also solve all the way for t dt, and then the 2 divided by 8 would be 1/4 inside the integral. Let's also find the bounds. So when t was 0, we're now going to have u, which is 1 plus 4t squared will be 1. And when t is 1, u is going to be 1 plus 4 times 1 squared, which will be 5. So we're now going to have the integral from 1 to 5 of, we'll have 1/4 times the square root of u du. And then the second integral is just integrating 2, so that'll just become 2t. And we're going to evaluate that from 1 to 2. So then our u to the 1/2, because that's what the square root of u is going to go to 1/4. We'll end up with u to the 3/2. We'll increase that by 1, and then we'll divide by that 3/2, which is really multiplying by 2/3. And then that's going to get evaluated from 1 to 5. Let's just work on evaluating that 2t from 1 to 2. So that's going to be 2 times 2 is 4, minus 2 times 1 is 2. Here, notice we've got the 2 on top and the 4 on bottom. So we really have 1/6. We're going to have 5 to the 3/2. And then we'll have minus 1/6 times 1 to the 3/2, which is 1. So just minus a 6. And we'll have plus 4 and minus 2. So 4 minus 2 is 2. So then 2 minus a 6, well, we can make 2 into, let's see, 12/6. So then we would have 5 to the 3/2 over 6 plus 11/6 should be our final solution. And we'll just leave 5 to the 3/2 since the square root of 5 is irrational. So in this one, the big takeaway is that idea of we needed to do a couple different things, where first we needed to create our parameterization, our piecewise smooth parameterization of our curve. And then in order to integrate over that parameterization, we had to split it up into the 2 integrals over those different piecewise smooth pieces.